Okay, now that you understand the basics, let's talk about something a little more complex. Let's say, for instance, we've got a coordinate system. Okay, again, we've got x and y. And let's say that we have, let's call it a displacement vector. We'll talk about a couple displacement vectors. Maybe we're going to say, we're going to go this direction, okay? And we're going to go that direction. And what I want to know is where is my final resultant, okay? My final resultant displacement. Let's say that we went for a total of, we were looking again for this final displacement vector, which is, which is this guy right here, okay? We're looking for the green final displacement vector. The issue is we need to figure this out. We don't really know a whole lot, and things are no longer, the big important thing is things are no longer right triangles. But we do know we're given, now let's say we went a total distance of 7 and a total distance of 8, okay? And let's say we ended up saying that this data here was going to be, let's call this first data, data 1. And let's call this data, data 2. And ultimately, we need to know the displacement vector, d, which again is a magnitude and a direction, which means that we're going to have some sort of number and some sort of angle. So the way we do this is we break this down to the things we know, right? We need to break this down into x's and y's so that we can ultimately get a final x and y here that is a right angle. So we need to break this down to things that we know, to right angles that we know. So we can look at this triangle and this triangle. Right? So we know that, hey, okay, if we can figure out what this x is and this x is, then we know that we say, okay, and let's call this displacement 1, and this is going to be displacement 2. So this is going to be d1x and d2x from here to here, and then d2 is from here to here. Right? And we know that this vector here is d1y, right? And then this is going to be d2y between there and there. And so together, so the big D, so d vector, resultant d vector x is equal to d1x plus d2x, right? And we know that d resultant y is equal to d1y plus d2y, right? And so now we just do some basic math, a couple of trig functions to get there. So let's say, and I'll do the first one, and the rest of it you're going to figure it on your own. So let's look for d1. So if d1 is a magnitude of 7 with a direction of, let's just say we would be giving you the direction. You're going, Mr. A, where's the direction? I know. Let's say the direction is, let's call that 75 degrees. And let's call this one 12 degrees. So theta 1 is equal to 75 degrees, and theta 2 is equal to 12 degrees. And what we need to figure out is d1x and d2x and d1y and d2y. So what we do is we say, okay, well d1, okay, is equal to 7, a magnitude of 7 at an angle of 75 degrees. So d1x, okay, is really the cosine, or 7 times the cosine of 75 degrees. Now, Mr. A, where do we get that? Well, let's look at this. I'm going to hide this for a second, and we're going to show this, okay? So if I have a triangle where I have this, this, and this, right? Where I'm saying this is 7, and this is 75 degrees. Well, I know that I have an opposite and an adjacent, right? And I'm looking for the adjacent, aren't I? So I say, okay, well, again, so, ka, to, right? So if I'm looking for my adjacent, well, which one has my adjacent? Well, it's either cosine or its tangent. Well, in order to do tangent, I need the opposite. I don't have that. But I do have my angle, and I do have my hypotenuse. I'm just missing my adjacent. So I'm going to write that a little clearer, 75 degrees. So what I can do is I can say, look, the cosine of 75 degrees is going to equal my ratio of adjacent over hypotenuse, okay? So adjacent is equal to 7 times the cosine of 75 degrees. And if I go back, remember, that's essentially what I did. I said that the adjacent, which is d1x, okay, is equal to my 7 times my cosine 75. I'm going to go back so you guys can see that again. This was my d1x. This is my d1y. And the same goes for sine. Let's say I have my opposite. I'm looking for my opposite. I have my hypotenuse and my angle. I can say the sine of 75 degrees is equal to my opposite over my hypotenuse, which means that 7 times the sine of 75 degrees equals opposite. So you can make these shortcuts, okay? You can make these shortcuts when you know that, and let me rewrite this so it's a little clearer. We can make it a little clearer. So opposite equals 7 times the sine of 75 degrees. And we make these shortcuts when we know we have to set up, so we have the adjacent equal, and we have this lower angle here. Our 7 is our hypotenuse and opposite and adjacent. So where our adjacent is our x and our y is our opposite. And we can make those sort of shortcuts. So we go back and we say, okay, well, d1x is 7 times cosine 75. So that means I'll come over to here and get my calculator. So 75 degrees, and I'm going to say cosine, okay, times 7 equals, again, it's like a percentage, right? It's equal to, what was that number? The number was 1.81. So d1x is equal to 1.81, whatever our units are. So that's our d1x. Our d1y is equal to 7 times the sine of 75 degrees. And again, you can notice that we're looking at x for cosine and y for sine when it's set up in this fashion. So now we can say d1y is equal to 75 sine of 75 times our 7. So it's about 90-something%. So we were at 6.76. And if it's all in meters, then it's all unit of meters. And now we can do the exact same thing for our D2, okay? So let's look at D2. So D2 is now, and we'll draw the D2 one for a second here. D2 looks like, again, if we have we remove our origin, okay? So that D2 is here, okay? Right, and I'm going to come back to this so we can see this. There's our D2 right here, and all I've done is shifted that entire vector down to the origin. Now this is really interesting. You should know that you can, in all cases, move these vectors around. As long as you keep the same angle and the same length, you can always move it, and it's just a matter of being relative to each other, because you're always going 10 feet in a certain direction from a certain point. So the vector is the same, just depending on where you start. So again, I'm going to come back to this. And so this was an angle of 12 degrees and a length of 8. So it was an angle of 12 degrees and a length of 8. Okay? So again, I can look at and this is D2, right? So D2y is this height, and D2x is this length. And again, we go back to our conversation when we said, you know, if we keep it in the position where we have our vector, our angle here, opposite adjacent, our hypotenuse, we can always say that the x factor is always our hypotenuse times the cosine of the angle, and our opposite always the hypotenuse times the sine of our angle, assuming that the angle is down here. If it's up here, it's a different scenario. You got to think about that. So now that I know that, I can say, hey, look, our d2x is equal to 8 times the cosine of 12 degrees, okay? So that means d2x equals 12 cosine times 8 is 7.83. This is 7.83. And our d2y is equal to 8 times the sine of 12 degrees. So I come back and I say, okay, 12 sine times 8, and it's 1.66. So d2y is equal to 1.66. Okay? And now, so now that I've got that, all right, I can figure out d, right? Because d is essentially, I'm going to come back to this. If I come back to this here. D is essentially, let's do this, right? Where we've got, this is our D vector, which is really d1x plus d2x is this length, right? And this length is d1y plus d2y, right? And that's going to give us, and so how do we get to d? Well, d squared equals this d1x plus d2x squared plus d1y plus d2y squared, right? So it's again, this is the Pythagorean theorem, and we just plug and chug. So if I look at our initial numbers, I'll come back to here for a second. Our d1, d1x, which is this one, this is going to equal d1x, and this is equal to d1y. So our d1x is sine, where do I have that? Do I have it somewhere else? 7 cosine 75, right? So d1, oh, here it is right here. So d1x, okay, was 1.81. d1x is 1.81 plus d2x. Well, my d2x is over here. d2x was 7.83, right? 7.83. And we're going to square that. Plus our d1y, which is 6.76, plus our d2y. And d2y was our 1.66. 1.66, and we're going to square that. And that's all going to equal our magnitude of our vector squared. So we can do some simple calculations here. So 1.81, 1.81 plus 7.83 equals 9.64. So I'm gonna take this now. I'm gonna actually bring this to a different stage. I'm gonna take this, I'm gonna copy it. I'm gonna go to a different layer here. Paste it. Oops. Here. Okay. I'm just going to kind of get rid of this so we can, take a look at that. Okay. So what we're going to do is we're going to say, okay, well, that means that our, if we go back to my calculator, the 1.81 plus 7.83 is 9.64. So it's 9.64 squared plus, and again we say 6.76 plus 1.66, oops, try that one more time, 6.76 plus 1.66 is 8.42 squared, right? So we'll go back again. Obviously you guys have the Whopper calculator, you can do this all on your own. 9.64 squared plus 8.42 squared equals 163. But I know d squared is equal to that, so d equals a square root of this, right? So that means that d is equal to the square root of this number, which is 12.80 roughly. 12.80. That's the magnitude of my vector. The question now is what is my angle, right? Because I still have to have this is my magnitude, but I need my angle. So in order to find the angle, what we need to do is we need to then do another trigonometry function. Well, again, what do we have? We have actually all three lengths. We have this length, and that length. So you can use either one, but any of the three. But I'm just going to use tangent because I've got these numbers here. So the tangent of my angle, here's my theta 2, right? Because that's what or actually theta 3, because this is our new theta. Because if we go back to our original piece, we'd have a new theta here, which is this angle here, which is going to be theta 3. Excuse the mess, guys. I mean, I apologize, but this is what ends up happening is you get very messy. I had a guy, college professor, used to mix colors. He got so messy. But we're looking for theta 3. So if I come back, oops, and now we're looking for theta 3. So theta 3 is, if I look at tan of theta 3 equals our opposite over our adjacent. So the dy, so that's 8.42 over 9.64. So that means that the inverse tangent of 8.42 over 9.64 equals our theta 3. So then we can come up to here and we can say, all right, the inverse tangent, so 8.42 divided by 9.64, oops, try that one more time, 8.42 divided by 9.64, and then we're going to say the inverse tangent. So I got to do my shift, so I can say inverse tangent, not hyperbolic, but regular tangent. Boom. That means our theta 3 is equal to 41.12. Theta 3 equals 41.12 degrees. So our total vector for D is 12.80 length, and let's say it's meters, so it's meters, at an angle of 41.12 degrees from the x-axis. And that's essentially how we do that problem. And so from here on out, I'm going to have you guys do a few problems just to get some practice.